Today's lecture is all about utility companies and how utility companies like to bill their customers. So with utility billing, well, when we're talking about doing energy audits and saving energy, that's great. I mean, that's a noble cause. However, our customers, they almost always care about the dollar signs. So how much energy are they saving versus how many dollars are they going to be saving? So if you do a project and you save, say, 100,000 kilowatt hours of electricity, and we'll talk more about kilowatt hours here in a moment, saving that amount of energy will be very, very different if your customer is paying 3 cents per kilowatt hour. We see that in central Washington, where they have hydroelectricity all over the place. Electricity is the cheapest in the country in central Washington, versus going to California, where they may pay 20 cents or even upwards to 30 cents. So for 1 unit of energy, we're seeing a potential disparity of, you could be paying 10 times as much depending on where you're buying your power. So at the end of the day, you might save a lot of energy, but if that doesn't equate to a lot of money, is your customer going to care? Maybe. I would say rarely, at least from what I've seen and the clients I've worked with. Occasionally you get customers who are super gung-ho about saving energy, and that is a goal in itself. But usually at the end of the day, they want to know, or they want it to be a good investment financially. So as an energy auditor, it's important to understand how these utility companies bill their customers so you can take that energy savings and turn it into dollars. And any audit you do, you're going to have to do some kind of review on how your customer is paying for their energy. Some typical line items you might see in a bill: you have your base charge, which is always going to be the same every month, which is essentially paying them for the privilege to be their customer. If you're looking at an electric bill, you're typically going to see that your bill based on usage and peak demand. We'll come back and talk about how those two terms differ. If you're buying fuel, most commonly natural gas, but with fuel, it's typically only based on usage. And the common fuel types you're going to see: natural gas, that's the big one. In more rural communities, you might see fuel oil or propane. But generally speaking, in commercial applications, it's natural gas. On your bill, you could see a rebate charge, which we'll come back to and talk more about. Potentially a transport charge if you're buying your energy from a third party. Basically means I'm going to buy my gas, let's say, from a company a state over, but they're going to feed that gas through somebody else's pipeline to get to me. So in this case, we buy all of our natural gas from Avista, and they pretty much have a monopoly around here. But theoretically, if we could buy our gas from someone in Idaho, maybe they can use Avista's infrastructure to get the gas to me, in which case I have to pay this transport charge to Avista for using their infrastructure. Going
So I had a
into,
quick question. What percent of like the billing is like the base charge usually?
it's usually
Just curious.
fairly small. Like, this is throwing it out there, but um, maybe a few percent at
Oh,
most.
not low. Okay.
Where it becomes a bigger part of your bill is So with natural gas, we typically use natural gas with heating. So in the winter months, we use a lot of gas. And then in the summer, we're using very, very little gas. And so what you see is that in the summer months, that base charge becomes a bigger part of your bill just because you don't have that usage charge, but you still have to pay the gas company to um, to be their customer. There are certain fixed costs associated with that, if that makes sense.
Yeah. Okay. Interesting. Thanks.
Yeah. So to dive a little more in depth on the electric side, I mentioned peak demand and usage. So the two terms here are kilowatts, kW, and kilowatt hours, kWh. And I don't know if you know the difference to this. I know this isn't something that I learned while I was at Gonzaga, but the main difference here is kW is power. I'm sure that's a term you've heard of. Kilowatt hours is a unit of energy. And the relationship between the two, kilowatt hours equals your kW times your hours. So a very simple light bulb example. Let's say we're feeding this light bulb 60 watts of power, or at least whenever that light switch is on, that's how much power it's drawing. But if we ran that for 1,000 operating hours, say in a year, 60 watts times 1,000 operating hours is 60,000 watt hours, or 60 kilowatt hours. And then that's what you would have to pay for from your utility company. The peak demand, which they measure in kW for your peak power draw, this is the highest instantaneous power draw seen in a billing period. So usually electric companies bill by month. So you'll have a bill for January, a bill for February. They'll look at that period and they'll see what was the highest power draw that you saw at your building in that period of time, even if it was only for a moment. And I'll have a visual representation of that here in a moment. And the reason they bill for this, the reason they care, even if it's only for a small period of time, all of their equipment that they use to generate that power, it has to be capable of providing that demand, that peak demand, no matter what, even if it's just for 15, 20 minutes. And that costs them money to maintain that equipment. And then electric energy. So this would be for the energy used in kilowatt hours, and they're going to bill for the total amount that you consumed. How much total energy did you use through that period? Typically in residential applications, like at your house, they typically don't worry about the peak demand because it's kind of hard for a house to use this really big demand at any given time. Houses are fairly predictable in how they use power and energy. But in commercial applications and industrial, they will typically bill you for both peak kW and total kWh. Utility billing is defined in what they call rate schedules. So a Vista, for example, they have a bunch of different rate schedules for different types of customers. So what I pay at my house is different than what Kaiser Aluminum pays for their electricity. And so they have these different rate schedules that apply to different classes of customers. And here's a sample electric bill. So this is a lot to take in, but to identify some of the main components of it, you have your billing period. So this would be November to December. The schedule name, so schedule 36, that is the rate schedule that applies to this classification of customer, your total energy used, kilowatt hours, 252,000, your peak demand. So at some point in this month, they drew 504 kilowatts of power, even if it was just for a little bit of time. And then you have reactive power, which is related to power factor. We'll come back to that. Then you have all of your summary of charges, and you can see all your kilowatt hours, kW, your kVAR for reactive power. It gets a little complicated, but at the end of the day, this customer paid a little over $19,000. And I think this was a community college campus meter. So they had one electric meter that served the entire community college. And that's how much they paid from November 22nd to December 26th. That's quite a bit of money.
Quick question. What is the meter multiplier?
Oh, the meter multiplier, this 2400.
That's the one.
So the way these meters work, they don't just spit out 252,000 kilowatt hours. The meter at the beginning of the period, November 22nd, the meter read 1,034. And this only ticks up by 1 for every 2,400 kilowatt hours. So there is some inherent rounding that goes on in here. So what they do is they read the meter at the beginning of the month, they read it at the end, 1139, multiply it by 2,400, and that gives you this usage. And then the next month, the previous reading would be 1139, and then they'd read whatever it ticked to from then. So to try to illustrate this difference between peak, kW, and kilowatt hours, if this was your building, and over time on your x-axis, this is the power draw over the day, let's say. Well, the area underneath the curve, so that represents how much energy got used. So if you have some extended periods of high power, that will equate to high kilowatt hours. But that peak power draw, that peak demand was 48. So for this customer, they would get billed for that 48 kW, even though there was only one time during the month where they hit that peak. It doesn't matter if it was only one time, they will still get hit with a charge because that generation equipment has to be able to provide that 48 kW at a moment's notice. So an example rate schedule, this would be a fairly basic one. Let's say you have a $50 base charge. No matter how much energy is used, just for the privilege of being their customer. And then they'll charge you 8 cents per kilowatt hour. That's a fairly representative rate in the Spokane area. That's about what we pay. And then maybe $6 per kW for that peak demand, but only that one-time peak demand. I like this analogy to think about it in terms of a rental car. Not that this is how they charge you to rent a car, but I think it helps illustrate the point a little bit. So let's say they're going to charge you a base fee just to rent the car, just to cover their administrative cost. Doesn't matter if you're going to drive that car 5 miles or 100 miles. You got that base fee. And then they're going to bill you for the number of miles driven. So that would be analogous to kilowatt hours. And hypothetically speaking, let's say this is some oddball company. They say, we're going to charge you for the peak speed that you drove during that rental period. Because for some reason, this car company wants you driving steady and slow. It's easier on the car, let's say. But that's a way to think about how utilities bill for electricity. On the natural gas side, they also have rate schedules, but typically it's a lot easier on the gas side. They're typically going to charge you in terms of therms or MMBTUs, which a therm is 100,000 BTUs. 1 MMBTU is a million BTUs. We're going to come back to that prefix of MM because there can be some confusion there. And one big difference here is there's not really a comparable demand charge like there is for electricity. The reason being, natural gas isn't produced on demand like electricity. It's a stored fuel, and they can send it out as needed. So they're only going to bill you based on the usage, but not on the peak demand. Piece of cake. There is kind of a parallelism here when we're talking about gas efficiency. Gas efficiency metrics, pretty simple compared to anything that uses power like an air conditioner. Another bill, but this one's for gas, but to identify some of the same components, we have the billing period, the schedule name, so schedule 504, general commercial service. There's their therms used in that month, so about 1,800 therms. You have a summary of charges, and then at the end of the day, they're paying about $1,500 a month at this building. Let's revisit input versus output, and thinking back to this generic process diagram that we talked about last week. This is something I stated before, but it's super important. It's really important to understand input versus output when you're talking about units of energy. Utilities bill in terms of input, so on the left side of this process diagram. And then the output side, that's the delivered useful output that we actually want. So if we're getting heat, that's how much heat we're going to get on the output side. Simple gas heating example. So let's say you have your building. You need 100 million BTUs to heat your building. So that would be the useful output. You need 100 million BTUs on the output side of that. And if you have an 80% efficient heating source, like a typical gas-fired furnace, you divide the two. So your 100 million BTU output requires 125 million BTU input, which equals 1,250 therms, which is what the utility company is going to bill you for. The reason I like to revisit this is one of the number one things I've seen when I teach this course is making the mistake of considering something an input or an output when it's not. So when you're reading the problem statements on the homework or on the tests, really think about, is this energy unit given? Is this on the input side, or is it the output, the useful output side? Some rate schedule types. The easiest one is a flat rate, which is the same rate every hour of the day, every day of the week. This is very common for any residential customer. A block rate, that's the next simplest one, where they're going to vary the rate depending on how much energy you use. So as an example, they may say, well, the first 10,000 kilowatt hours, we're going to bill you at rate 1. And then the next 10,000 we'll bill you at rate 2. And then from there on out, we're going to bill you at a third rate. So a common example of this would be the first 10,000 kilowatt hours, they will bill you at a higher rate. And then as you use more energy, I guess you can think about it like a bulk discount. And so the rate will actually get cheaper the more energy you use. And it's important to note here that first 10,000 kilowatt hours will always be billed at the rate at rate 1, and then the next block will kick in. But if you were to use 30,000 kilowatt hours, it wouldn't all just be billed at rate 3. You would have some of that billed at rate 1, some billed at rate 2, and so on. You could have an on-off peak rate where they vary the rate depending on the hours, night or day. Where we see this is in hotter climates, where there's a lot of air conditioning use, like in Arizona, for example, 120-degree days in the summer. So what they might do is say, well, from 12 p.m. to 6 p.m., that is our on peak, because that's the hottest part of the day. That's when our generation systems need to be full fire, putting out everything they can. So we're going to charge a higher rate. And that could also factor into where that electricity is coming from. So maybe at nighttime, they can rely more on, say, wind turbines. But then once they get into that peak of the day, that's when they need to fire up their gas-fired power plants. And so that would justify a higher rate. The off-peak would be any of these off hours. So from 6 p.m. to 12 p.m., they're going to charge a lower rate. And so there could be some incentive here to trying to shift your building use into that off-peak period and take advantage of that lower utility rate. They also have a seasonal rate, very similar concept to the on-off peak billing. The only difference here is this is based on months. So same idea, higher rate in the summer, lower rate in the winter, but it's not as granular as the on-off peak rate, which varies by hour of the day. This is more just varying by the month. You could have an interruptible rate. This is kind of a specialized rate schedule. But what this does is they say, we will give you a lower rate, so your bill is lower. But if we are in a position where we are running out of capacity, you allow us to cut service to your building. And maybe the customer is okay with that. The utility should be giving them a heads up. It's not like they'll just be working in the middle of the day and then all of a sudden they lose power or gas. But that could be a very attractive deal depending on the client. The rate schedules can be very complex. If we look back at those electric and gas bill examples from before, there were about 10 or 12 line items that all added up to that final thing at the bottom. They can be really complex, and you can have a combination of all of these rate schedule types. So you could have a seasonal rate that also has block rates built in, or a seasonal rate that also has the on-off peak in there. Fortunately, where I've done the bulk of my work here in Spokane and the Pacific Northwest, we typically see block rates and that's it, which is a pretty easy rate schedule to work with. If you get into the on-off peak where it changes by the hour of the day, that gets a lot more complicated in trying to do those calculations and figure out how much money is my client going to save. Some quick unit conversions. I can't remember if we've talked about this one yet, but 1 kilowatt hour is equal to 3,412 BTUs. A little debate there. Some people use 3,413. It's got something to do with the specific heat of water, but the specific heat of water changes slightly depending on the temperature of the water, or something like that. But whichever one of those you use, it's a minuscule, almost negligible difference. But if you see one or the other, that's why. We mentioned a therm being 100,000 BTUs. And then we get to this M prefix. So when we're dealing with the metric system, M means mega, which means a million. When we're talking about electricity, usage and demand, which is based in watts or kilowatts, watts is a metric term. So in the case of electricity, M means mega, which means a million. So 1 megawatt hour is equal to 1,000 kilowatt hours, or a million watt hours. Usually we're dealing with kilowatt hours, unless you're getting into very large buildings, in which case you might speak in terms of megawatt hours. So that's the metric system. The imperial system, or inch pound system, the Roman numeral M means 1,000. And this is typical when we're talking about fuels and gas, because fuels and gas is always expressed in terms of BTUs, and BTU is an imperial unit. So what that means is 1 MBTU doesn't equal a million BTUs like you might think. And I've had countless conversations with junior engineers who go into this field, and they just learn to accept that an MBTU is 1,000, and they just say, "Yeah, that's weird," and they just go about their day. And then finally, it comes up randomly, and they're, "Oh yeah, I always wondered about that, but never looked it up." But that's why. So 1 MBTU is also a KBTU, even though the K prefix is more of a metric thing. We still see that used a fair amount, which is 1,000 BTUs. So then we get to the BTU, which is a million BTUs, 1,000 BTUs, MM. And then when we're talking about BTUs per hour, which is often the case when we're talking about how much gas heat output a heater is capable of, how much heat can this heater output? It's usually expressed in BTU per hour. The input can also be in BTU per hour. So BTU per hour offhand is shorthand written as BTUH, and then MBTU per hour, 1,000 BTUs per hour, is often written as MBH, all capital. So this can be a little confusing, but this is the way it's been. I don't think I'm going to change anyone's mind, so get used to it. Rebates. So you've probably heard of utility companies offering rebates for projects that save energy. Why would they want to do that? If their job is to sell energy, wouldn't they want to sell as much energy as they can? I mean, isn't that the general business practice? I want to sell as much of my product as possible. But a rebate is saying, we are going to reward you for using less of our product, which seems kind of backwards. The reason they do this, they are often obligated to. Usually it comes from the state. So the state is coming in and saying, you need to incentivize your customers to use energy. And there may be some specific standard methodologies to apply those rebates, or they may say you need to spend X amount of dollars in rebates this year, or else we're going to get angry with you. I don't know what would actually happen in that case, but yeah, it's often obligated for them to provide these rebates. But there is one reason why a utility company might want to do it as well. The reason being, if they don't reduce that energy use, I mean, energy use is only going up. So if we can't curb that increase, they're going to need to build new generation plants, which costs them a ton of money. So from their perspective, let's maximize our income from what we got as long as possible. So there is some reason for them to offer these rebates. And who pays for them? Well, that comes from their customers, from you and me and all of our clients. It might be an explicit line item on a bill, or it might just be buried within that that given rate, just kind of hidden in the background where you don't really see it. But ultimately, in the utility companies, they're certainly not going to want to pay for it. So ultimately, it comes from us. A couple different types of rebates. The two main ones are what's called prescriptive versus custom rebates. Prescriptive rebates are very easy and simple. You install something, get paid. Most common example would be for lighting and motor upgrades. And it's typically calculated based on some fixed or known quantities. So using the lighting and motor examples, maybe you get a certain amount of rebate dollars per lighting fixture or per horsepower of motor. You typically see this when energy savings are relatively predictable. So the calculation here is very simple. Hey, you installed a 50 horsepower motor. I'm going to give you $100 per horsepower, piece of cake. However, the other option, which is the custom, another name for it is site specific, is they will give you a certain amount of dollars per kWh or therm that you save in the first year. And this is typically for anything that you're doing at this building that's not so easily quantified. So the reason they call it site specific as another name is this is essentially a unique project to this building or system that doesn't really fit into a box. So this is going to require some detailed calculations to determine those energy savings. You can't just say you installed 100 horsepower of a super efficient motor. You actually need to do a detailed calculation to come up with how much kWh or therm is going to be saved in that first year of operation. This is often used with control strategies. So if you're going to make a bunch of changes about how this HVAC system operates, you can't really put that in a box. You'll have to do some of these detailed savings calculations. Another big component to the custom or site-specific rebate is typically you have to prove those savings. Back to the prescriptive rebates, if you upgrade lights or you upgrade a motor, they know that that's going to save energy. They've done the math already. It's already predictable. With a custom incentive, you need to prove it. Even if the calculations show it's going to save this much energy, a lot of times they want to see your bills before and after. And so sometimes that means waiting a full year between when it gets installed and when you get your rebate.
But wait, let's say you're like also installing a bunch of new stuff, so your building's just going to use more power. Would you not get any money back then for upgrading?
Actually, there is a potential incentive there. And I think actually the homework has an example that kind of relates to that. But to give you an example, let's say you have a building that isn't air conditioned today, has no cooling, and you want to add an air conditioner. Well, you know that that's only going to increase your energy use. But let's say code says your air conditioner has to be at least 10 EER for your efficiency. And what if you instead opt to put in a 13 EER air conditioner? Yeah, you're going to have to pay more money for that high efficiency unit, but it's better than what code would require. So there could be some savings there. And usually that would fall in the prescriptive bucket, where they might just say, well, for every point of EER you are above code, we'll pay you $500. Does that make sense?
Yeah, thank you.
So load factor, another term to throw at you. This class is full of terms. Load factor, defined as your average kW, so the average power draw of your building over some period, divided by your peak kW. So we've already talked about peak kW. That would be your peak demand that your utility company sees. Your average kW, that numerator term, so that can be calculated if you know your total kilowatt hours, and then you divide by the number of billing days multiplied by 24 hours a day. So if you take your total kilowatt hours used and divide by total hours in that period, that'll give you your average power draw in kW. I'll have something to illustrate this a little better, but a low load factor is going to indicate a higher average cost per kilowatt hour. Reason being, a low load factor means that your demand charges, your peak kW charge, makes up a larger portion of your bill, which increases the average cost. So this can incentivize you to spread out your load throughout the day. If you can spread out your load to make it more even throughout your day, you can reduce your electric bill for the same usage. So if you had two buildings here, so one building, their power draw is in blue, the other one is in orange. Both of these curves use the same amount of energy, which would be the area under the curve. So they're both using about 1,700 kilowatt hours over a typical day, which is about 50,000 kilowatt hours in a month. But which one is going to pay less? So the first building, well, they only had a peak demand of 77 kW. The other building had 170, so significantly higher peak. But ultimately, that blue load is spread out more evenly throughout this period, which means it has a better load factor. The second load has much higher demand charges, so they're going to pay more money for the same amount of energy. So here's an example, a mathematical example. So assuming those same buildings we were just looking at, let's say they have 30 billing days, 50,000 kilowatt hours of usage for the month. And we'll have some sample electric rates in here. So the first building, their bill, assuming 6.5 cents per kilowatt hour, so a little over $3,000 for their energy, assuming $6 per kilowatt on the peak demand, it's another $462. So their total bill at the end of the day, about $3,700. And if you were to think about this in terms of the average cost per kilowatt hour, so you take that total bill, divide by the total usage, they're paying about 7.4 cents per kWh. Their average kW, so you take the usage, divide by the days times 24, average kW is about 69.4, and then we can calculate their load factor. 69.4 over 77.9. So load factor is always from 0 to 1. A 1 would indicate a hypothetically perfect load factor, essentially a flat line on their use. The second bill, go through the same steps. Their energy component of their bill is identical, but now their demand, they're paying quite a bit more in demand. So $1,000 as opposed to $462. So their total bill increased, which means for the same amount of power, they're paying about 15% more because of this poor load factor. To calculate their load factor, well, the average KW, that's the same because that's based on their usage, same number of billing days. But because their peak demand is 170, significantly more, their load factor is 0.41. So substantially less than that first building. So there can be some incentives here to try to spread that load out more evenly throughout the day. Or if you could couple this with an on-off peak rate schedule, and there may be some additional advantages there where, hey, maybe we can run some of our process equipment overnight. Let's run a night shift instead of running it in the middle of the day when we pay a lot more for energy. Next term I'm going to throw at you is the power factor, which is often confused with the load factor. Power factor, also expressed from 0 to 1. I hope you learned this in, I want to say, one of your physics classes, but watts is equal to volts times amps and times power factor, which low power factor is caused by the voltage and the amp sine waves getting out of sync. Normally I would draw this on the board, but a little hard to do from here. Amps are always going to follow voltage. So in America, we have alternating current power. And so your voltage at any outlet in your house is based on a sine wave. And when something is applied with a voltage, it will induce a current. And then the amp will also have a sine wave, but they aren't entirely in sync. And that's where this power factor deal comes from. The utility company, they have to produce more power at their generation source than what's actually required at the end use. So if you have a motor at your building that draws 10 kW of power, the utility may need to generate 12 kW to serve that 10 kW of power. It's kind of back to that idea of input versus output. They need to produce more than is actually needed on the back end. And the lower the power factor, the greater this disparity is. Utility companies, they don't like this. The reason being, a low power factor is not accounted for in kilowatt hour metering. So this 10 kW of power at your motor, that's going to be the basis of your meter energy use, even though the utility has to produce 12. So to the utility, that's still a cost that they have to account for, and that's why they don't like it. They don't like buildings to have low power factor. We'll talk about what causes that here in a minute. And sometimes electric utilities will penalize, they will charge their customers if they have low power factor, because ultimately the utility company is who ends up paying for that low power factor. And this is represented on a bill as kVAR, which is kVA reactive, and a high kVAR is bad. If we were to look back at that electric bill example earlier on, you would see a line there that mentions the kVAR. And I believe there was even a charge for it. Oh, so here's a picture of that sine wave. So we apply a voltage to something, and then the current comes after. And so there's always this offset between the voltage and the induced current. And if you were to draw a vertical line moving from left to right, the power is the product of the voltage times the current. So what ends up happening is when your voltage peaks, your current hasn't peaked. And then your voltage starts to drop, and then your current peaks. So to get the best output out of AC power, you want those sine waves as close together as you can. And the further they get apart, the worse the power factor becomes. And you have to generate more power at the generation source to deliver some amount of power at the end use, at the motor or the light or whatever. The big thing that causes low power factor, anything with magnetic properties. The two most common examples in a commercial building are large induction motors, and most motors are induction motors. The other thing that we often see is magnetic ballasts in lighting systems. We don't see a ton of magnetic ballasts anymore, and we'll talk more about ballast when we get into lighting, but the ballast is basically the brains of a fluorescent light system. And the older style ballasts were magnetic. Nowadays, they're all electronic for the most part, but we're working in old existing buildings, we still might see magnetic ballasts. Fortunately, we can correct a low power factor with capacitors. If you place capacitors in line with the electrical system, that will actually bring the sine waves back together. There's a homework problem that talks about this, but the fundamental steps are, if you take the power draw of a device, say a motor, in kW, you just need to multiply it by a correction factor to get a capacitor size, which the capacitor is sized in kVAR. And those correction factors are looked up on a table, which in the homework, I gave you this table. And all you need to know is what your starting and your desired power factor is. So if you measure your power factor at 0.6, you look up 0.6 as your starting point and say, well, I need to get up to at least 0.9. You look up 0.9 going the other way on the table, and that gives you a multiplier to size your capacitor. So to get your attention, this is probably my favorite analogy in this whole course. So if you think about a glass of beer, you order a pint of beer, but do you really get a pint? So the three terms here, you have real power in kW. That's the beer. That is the useful thing you get out of that pint. The real power, kW. The apparent power, which is expressed in kVA, that's the beer plus whatever foam or head you get on the top of the beer. The reactive power, which is the thing we don't want, is the kVAR, the kVA reactive. So that's the foam. So you go to a bar, you pay for the whole pint. You pay for the kVA, which is the real power, the beer, the useful thing, and the reactive power. So you pay for that entire thing. I say you pay, really it's the utility company who's paying for it. But the foam on the beer, that's an inherent part of the process to deliver that beer. We can't get away from it. or at least you certainly wouldn't want beer that didn't have any head on it. Some head is okay, but if you got a pint glass that was half beer and half foam, you're probably going to be a little upset. And so this is hopefully to help illustrate kind of how the utility company is thinking about it. With power factor, we have this what we call the power factor triangle. But first, I guess another way to state power factor is the real power in kW divided by the apparent power. So that real power being, what does the end use see? What does the motor see? And what are we billed for by the utility? And that apparent power, that's what the utility company has to generate. So to put that in this power factor triangle, I mentioned kVAR is bad. We want this kVAR section of the triangle to be as low as possible. And as this becomes lower, the apparent power that the utility has to generate starts to become equal with the real power. But the more reactive power we have, the more these become out of alignment, and you need a lot more apparent power to deliver some real power. The reason this is expressed in a triangle like this, you can break out your trig books. kVA squared is going to be equal to kW squared plus kVAR squared. So if you know two of these terms, you can solve for the third term. Also, if you have this power factor angle, this theta, the power factor is the cosine. See, is that theta? I think it's theta. Is the cosine of that angle. I tend to try to avoid this cosine approach because I always seem to mix up my calculator on if it needs to be in radians or degrees. But the Pythagorean way, that's pretty bulletproof. And you might notice that all three of these components, kW, kVA, kVAR, they're all essentially the same units because volts times amps equals watts. So kilowatts, kilovolt amps, kilovolt amps reactive, they're all essentially the same units, but they are given distinctive names because they are referring to different things. Quick example, let's say you have a induction motor and you stick your power meter on it and it tells you this thing is drawing 52 kilowatts at a 0.82 power factor, and you are curious, what does a utility need to provide in kVA and kVAR? So the power factor is kW over kVA. We can rearrange that to say kVA is equal to kW over our power factor, which we know both of those terms. So the utility needs to generate 63.4 kVA to deliver 52 kilowatts. And then if we use the Pythagorean method, we can rearrange that to solve for kVAR because we know the other two terms. Run through the calc, 36.3 kVA reactive. And so now you have all three components to that triangle. All right, last two slides, and I'll let you go. So we've talked all about how utilities bill their customers. What can we do to save some energy that's related to the utility? One thing you may be able to do is change the rate schedule. This is pretty rare, but sometimes can be done, where you might find out that a customer is classified into the wrong rate schedule. Maybe the building they're in used to be something else, and they changed the use, but for some reason their rate schedule didn't get updated. Like I said, it's rare. I think there's only one time I've seen this happen, but it's a very low cost way to do it. the basis of savings here, reduce cost of energy. You may be able to change your third-party seller. I mentioned early on, kind of briefly, this transport charge, where in certain markets, you can buy your energy from somebody else. You can shop around. I think this is a much bigger deal in Texas. In Washington, this is not something you can really do. But by doing this, you can reduce your cost of energy. And there are energy brokers out there to try to arrange these deals. And it's a negotiation game to try to get the lowest cost for your factory or whatever you need this energy for. Maybe you can shift to off-peak operation. If rates are lower at night, hey, let's run a night shift. Let's take away one of our day shifts, which again, reduces our cost of energy. You're probably noticing a pattern here. You could try to improve your load factor. So spread out that use through the day, get rid of those big KW spikes. One important thing here is by doing this, you may need to spend more kilowatt hours, but you may ultimately pay less due to those reduced demand charges. One example is, let's say you at night you produce chilled water, which you then need to use throughout the day. Well, instead of producing that chilled water in the peak of the day, how about we produce that chilled water at night and then put it in storage and then just hang on to it until the next day? Well, as that chilled water sits in that storage tank, it's going to be heating up slightly just by nature of heat transfer. And so that may lead to a little more kilowatt hour use, but you might be able to make up for that and more by reducing that peak demand. You might be able to increase your power factor by installing capacitors on those large inductive loads. And this is usually done at specific large loads in the building and not necessarily right at your service. The reason being, if you have, say, 10 large motors in a factory that could be kicking on and off at different times, your overall building load factor can be a little, can be highly variable, which these capacitors may have a hard time accounting for. Whereas if you put it at the individual loads, that's a more predictable place to place these capacitors. They do create, or they do make a specialized capacitor system that you can put at the point of service, but it involves a lot of complicated controls to account for those the changing loads throughout the day. And important caveat here, this only applies if the utility actually bills you for a low power factor, and not all of them do. So by doing that, you can reduce your power factor charges. Okay, that's all I got for today. Ran a little bit longer than usual this time, but I'm happy to stick around for 5-10 minutes, answer any questions you have. Otherwise, you are free to go.
Thank you.
Thank you.
Yep, thanks.
Thank you.
Thank you.
Thanks, Professor.